Section 1015 is called introducing per unit method. And I gotta figure out which way to turn my head. The point of going through this is to put some practical, real value to this per unit notation that we have learned back from earlier in our studies, all the way back to ELC 135. And we'll apply it. We will apply it specifically to transformers, and I think it will help you see some of the usefulness in making comparisons for per unit. Okay, so let me bring up some tables here for us to look at. So again, per unit notation is often encountered when we deal with transformers and other electrical machines. And the reason is that the per unit values gives a feel for the relative magnitude of impedances, voltages, currents, powers. And instead of dealing with ohms and amps and volts and kilowatts, we simply work with numbers and make comparisons. We don't have to carry along units because per units are, their ratios and their comparison methods. So the per unit method is applied to transformers is really easy to understand. And he mentions that, if you don't remember per unit, that it might be a good time to go back to section 1.9 to 1.11 in chapter 1 and look that up. But he says, let's begin by looking at table 10A, okay? And so table 10A is this table, and this is actual transformer values given to us. And you can see the actual values, what else is here in R1, all the parts of this transformer as we went through, the different models of that, it's all given to us across there. And we've got 5 different values in terms of the kVA ratings across the top, from 1 kVA all the way to 400,000 kVA. All right, and in scanning the table, we see, for instance, that for the magnitudes of impedances, let me clear this out for us so we can see this clearer. Come on now, don't be lagging on me. I'm having to use a hotspot here today, and it's not quite as fast as regular internet. But anyway, impedances range from, he mentions, what's the first one here that we're looking at? 505. Okay, so here, right? So we've got, that sort of range. So it's a very large range difference across there. I'm not seeing the 0.03. 0.0003. I don't see that on here anywhere. 0.003. Gosh, I guess it's here, but I don't see it. He references in the text. Let me pause this and see if I can find that right quick. Hold on. Sorry, it was right here all the time, right? So what he's saying is, it's a wide range that's explored in the table, and so he says in ratios of 1 billion to 1, from 0.0003 to 505,000. There's no recognizable pattern to any of the values because we're actually using these numbers. And, so the actual values, we really can't get a good feel for it. So with that said, you look at this table, you see a lot of numbers. They seem to be just all over the place, right? I'm here and I'm here, and I can't see patterns. So he says, what if it, instead of expressing R1 and R2 and XFF1 and XFF2 and XM and RM, what if we express them relative to another ohmic value, and what would that be? Okay, so he says the best approach would be to employ the nominal load voltage and current of the transformer, which we can calculate its value and use it as a reference. For example, and let me go to the writing point here. For example, in the case of the 10 kVA this guy, we could determine what the nominal load is for this on the secondary side by looking at NSF divided by INS, which would be here, and that is going to be 347 volts divided by 28.8 amps, and I get 12 ohms of resistance. Okay, so using this ohmic value as a reference, a relative value of the secondary resistance, R2, is available. And the way that we can approach that, and the way that we could use that, is we'll look at the value here and go at it with that approach instead of the actual values. So for our particular example, you know, if I'm looking at R2, I'm going to say 0.095 divided by our base. We're calling this our base is 12 ohms. Okay. And when we do that, we come up with a number of 0.0079. Okay. Now, what we're going to do, you know, we're going to use that number and plug it in over here in this per unit transformer table, and there's that number right there. Okay. Now let me go back to this, and we'll work through another one of these. He says similarly, the load impedance on the primary side is 2400 here, 2400, and that is divided by 4.17 amps for IMP. Getting a little sloppy here. And that comes out to be, he says, 576 ohms. Okay, we can see that raw value here for that particular number as we look at our, you know, we've got that actual value, so we can go back now and we can utilize that number to develop another per unit value number. Okay, now, you know, taking that derived 576 ohms that we got from the primary voltage and primary current, we come up with 576, and we divide that by the base, and there's where we could come up with our relative primary resistance, R1. This is 5.16. That's the number that we get when we do that. Then, you know, taking, you know, that value, and then we divide that by the value that's given. Let me back out of this, and I've sort of stumbled through this. Let me reiterate, as they say. Okay, so I rewrote with the values so we could go through this. I know that was getting kind of confusing. So the total, or the nominal load impedance on the primary side is ENP 2400 divided by IMP, and I get 576 ohms. Okay, so that's the nominal load impedance. Using this load impedance as a reference, the relative value of the primary resistance, is that primary resistance divided by this nominal value that we came up with. And again, what we would do is we would replace the actual values with that number. Where'd it go? Here. No, wait a minute. Here, 5.16, yeah, 0.0009, and that is here for R1. Okay, so that's what you're doing with this. You know, you're getting nominal values based on nameplate stuff, and then you're building this per unit chart. Okay, so R1 and R2 per units are pure numbers. They have no units, ratio of two quantities. So circuit elements on the primary side are always compared with nominal load impedance on the primary side. Similarly, circuit elements on the secondary side are compared with nominal load impedance on the secondary side. And proceeding this way for the other impedances, you can get all these different relative values calculated. And I know you're worn out on this stuff, so we won't go through any more of these and all. But what we're eventually getting to is this table. Okay, where'd it go? This guy, per unit transformer values. All right. So what can we see from that? All right. So in examining the table, the reader will note that for a given transformer, the values of R1 and R2 are nearly the same in a per unit environment. That and that are basically the same. Similarly, the values for XF1 and XF2 per unit are almost the same, right? 0.0056 and 0.0055. Now, that's not obvious. That's not obvious here, right? I mean, it doesn't just jump out at us when we're using the actual values, but when we look at it in terms of per unit and make a comparison, to that, we can see that they remain this consistent across there. Okay, and then there's even a similarity between per unit values of transformers whose ratings are quite different. Okay, the R1 for the 1 kVA is very similar to the one of the 1000 kVA, right? So bing and bing. Now we look at the other slides here, we sure don't see that in this, right? We don't see that connection here that in terms of relative values that we see with the exact values. All right. So the per unit values gives us that it gives us that look to see how the consistence of these things are. There are some things that as you look at this, here's that current that we talked about that accounts for the core and losses, the winding losses, and you can see here that those values they don't deviate a great deal, but man, they sure do here, right? So relatively speaking, based on the size, it's pretty consistent across there. And that's kind of what we wanted to walk away from with this. I think at this stage of the game, it might be beneficial for us to move on to other things. And, so we're going to do one more module, and then we'll be done with this chapter 10. Yay for you. And get on to other fish to fry. Okay, we'll wrap this up now.